So far, we have learned the estimation and the assessment of linear regression models. It is important to understand the assumptions of the linear regression model. The simple linear regression model imposes several conditions. We should verify that these conditions apply to the situation being analyzed before proceeding to interpret results. Although these conditions concern the population, they can also be observed in the sample. Here I present the observed residuals if all assumptions are true. Note that all the points are randomly dispersed around the zero value of the residuals. Also, there is no evidence of outliers because no residual stands out from the rest. Any discernible pattern of the residuals indicates that one or more assumptions have been violated. So we have 6 assumptions. The first assumption is the relationship between y and x is linear. So that means if we plot y, our response variable, against x, then the observed pairs are going to be dispersed around a linear line, either positively sloped or negatively sloped. The second assumption is the sum of all error terms is equal to 0, and hence the error term has 0 expected value and constant variance for all the observations. And as you see here in this figure, half of the error terms are above the 0 line and almost half are below the 0 line. So we expect that if we sum error terms, sum of all error terms will be close to 0. Assumption 3, the error terms are independent of each other. If the error terms are not independent of each other, you will see a discernible pattern, like error terms are going up and down together, moving together. But as you see here, they are randomly dispersed around 0. Assumption 4, there is no exact linear relationship among the predictor variables. Let's say you have x1, x2, and x3, 3 predictor variables. So x1 and x2 shouldn't be correlated, x2 and x3, and also x1 and x3 shouldn't be correlated. Assumption 5, the error term is not correlated with any of the predictor variable. Your error term should be also correlated with any of the predictor variable. And finally, the error terms are normally distributed. So to determine whether the regression model is appropriate for the data being analyzed, we can check the residual plots. We can plot errors against either the independent variable, like in this figure, or the predicted values y hat. But we do not plot error terms against the actual data. So in the next section, we will talk about violations of the assumptions. The first one is nonlinear patterns. Linear regression assumes a linear relationship between the response and the predictors. The simple linear regression model, say y is equal to beta 0 plus beta 1 x1 plus epsilon, implies that if x goes up by 1 unit, we expect y to change by beta 1 irrespective of the value of x. However, in many applications, the relationship cannot be represented by a straight line and therefore must be captured by an appropriate curve. In this section, we will analyze the happiness data. A sociologist wishes to study the relationship between age and happiness. So he interviews 24 individuals and collects data on age and happiness, measured on a scale of 0 to 100. So here, happiness is equal to beta 0 plus beta 1 age plus epsilon. And regression model is going to estimate beta 0 and beta 1. We start the analysis with a scatter plot of happiness against age. So we come here, choose insert, and then choose a scatter plot. And this creates a placeholder for a scatter plot. Then right-click and select data. And we add entries. The first one is our x values, in this case age. And second y values are our happiness. And click OK. Here in this chart, if you draw a linear line, you realize that this linear line doesn't fit to the data. But what we can do is choose a trend line, but the not linear one. Come here and choose more options, and then choose polynomial. And note that the polynomial line or quadratic line fits the data better than a linear line. This is the first way. You can plot your y variable against x variable and see the relationship between y and x. The second way is we are going to plot error terms against predictor variable age. To do that, click on data, data analysis, regression, and now our input or response variable is happiness and our x or predictor variable is age. We include labels Let's say we want the results to be in cell D1 and we want residual plots. Click OK. Here you can see the residual plots. It shows that there is an obvious trend with the residuals decreasing until the age of 50 and steadily increasing thereafter. The linear regression model is inappropriate as it underestimates at lower and higher age levels and overestimates in the middle. Residual plot is the second way of determining whether there is a linear relationship or not between the variables. The next violation of assumptions is changing variability. Recall that one of the assumptions of simple linear regression is that variance of the residual is constant across observations. Changing variability occurs when the variance of the residuals is not the same across all observations in the sample. In this section, we consider a simple regression model that relates monthly sales, which our sales are in $1,000, from a chain of convenience stores with the square footage of the store. So to understand whether there is a changing variability or not, we are going to plot the residuals against the independent variable. In this case, our independent variable is square fit. On the presence of changing variability, regression residuals will increase as the independent variable increases. So we come here, data, click on data analysis, and then we have regression, click OK, and then here we choose our response variable or dependent variable, and next we choose square fit, and labels are included. Let's say we want output in cell C1 and then we want residual plots. Click OK. Let's make this graph bigger. Now you can see the residual plot of the estimated model. Note that the residuals seem to fan out across the horizontal axis. Therefore, we conclude that changing variability is a likely problem in this application relating sales to square footage. This result is not surprising because you would expect sales to vary more as square footage increases. For instance, a small convenience store is likely to include only bare essentials for which there is a fairly stable demand. A larger store, on the other hand, may include specialty items, resulting in more fluctuations in sales. So what are the effects of changing variability on regression analysis? First of all, standard errors of the parameters are not reliable. Coefficient estimates, as you see here, square foot and intercept, are not affected. But if the standard errors of the parameter estimates are too small, but the coefficients are not affected, then the T or F statistic will be very high, indicating a frequent rejection of null hypothesis of no relationship. The opposite will be true if the standard errors of parameter estimates are too high. So as you see here, the standard errors are too low and therefore the t-stats are too high, and you are going to say, okay, there is a relation and a strong relation between square foot and the sales, but it may not be true because we have the problem of changing variability. And what is the remedy? So researchers use regression estimates along with a correction for the standard errors, often referred to as robust standard errors. Unfortunately, the current version of Excel doesn't include a correction for the standard errors. However, it's available on many statistical computer packages, including R.